This year chaired by Renata Teixeira and myself, Jörg Ott. Renata couldn't make it to this meeting, which is unfortunate, but we'll deal with this. You don't need too many people standing up here anyway. Since this is just our second iteration, I want to have a brief recap on where this came from. So the entire workshop has been coming out of a one IRSG dinner event where we talked about how to connect IETF and IRTF and research people better so that those communities have a chance to mingle somewhat more. And so we put together this workshop being outlined as a forum for researchers, vendors, and so on, to discuss emerging results in applied networking research. So the idea is to find a place and a framework that allows people from the academic community to actually submit their work to a place that's close enough that follows peer review guidelines and so on, but is close enough to an IETF to make it interesting to maybe stay over and take part in the remainder of the week. And we are particularly interested in applied results that could help us influence, add to, or otherwise interact with the IETF work, and also with possibly upcoming research group activities and the IRTF. So that's just the rough framework. We are trying to run this on the Saturday before the IETFs. The first two occurrences have been the summer IETF. There's no need that this would need to be the summer IETF. This is something that we can surely discuss later this afternoon, and I'm more than happy to take suggestions on this, me or other members of the steering committee. So for this year's edition, we got 20 submissions, which is a bit lower than we expected. We had each submission reviewed by 3 PC members. We had a conference call to discuss, and in the end, we decided to accept full papers, 7 full papers, 3 short ones, sorry, and 1 demo. And last year we had a relatively crowded program, so we decided to go this year to bit towards the other extreme, so we have plenty of time for discussion. We have lots of people from the IETF community here who are anyway eager to discuss pretty much everything all the time. So this should give us a good frame, so feel encouraged. We'll tell you when we run badly over. All papers are available open access on the workshop site and in the ACM digital library. And again, as for today's format and the stuff that we had, we're happy to take feedback in the evening. We have a program committee of a crowd of people who have been putting in cycles to do the reviews, discuss with each other so that we could finally come up with a conclusion of our program. That's those folks. The ones whom you might be, thanks to all of them for reviewing. The people you might want to talk to about suggestions for the workshop, future places, volunteering to chair it, and so on, are those on the steering committee, which is Lars Eggert, Matt Ford, Alison Menken, Colin Perkins, and myself. An important element of our little workshop, since we get coffee breaks and we even are going to have a reception in the evening, is that we get sponsors. Akamai and Comcast have been providing substantial support, as has the ISOC and also SIGCOM. From them we have received funding for allowing to put out some travel grants. So we had handed out a few travel grants, several students applied. One student unfortunately could not make it in the end due to bad circumstances in last minute. But we have a few travel grant recipients. So thanks to all our sponsors as well. And then for our agenda, so this is a relatively relaxed one. So we have a few minutes left for the opening. Then we have 3 technical sessions, 1 on measurements, 1 on transport, that also features a demo paper. This demo paper thing is going to be an experiment. The paper didn't quite fit as a full academic paper, but we figured it would make up a nice demos. But since this was the only demo that we would have had, putting it somewhere in the corner and hoping that somebody might notice didn't seem to be a good idea. So we'll do it. We'll try to do a full screen live demo for all of you and see how this goes. Then we'll have some lunch. Lunch will be catered in one of the adjacent rooms here, so we don't have to walk around very far. Next session is then going to be implementation and operations in the afternoon, and then we are going to close with a panel on internet health metrics. This came out of a submission that Leslie Daigle put in, where we said this is an interesting paper, but it would actually be much more suited for a discussion round, for a panel. And so we invited her to put together a panel, and she found 3 happy panel members for us, and we are looking forward to this as a close of the day. We'll do a quick wrap up and then move to our reception. So last year, this is probably hard to beat, that FU Berlin put together a barbecue somewhere outside. I don't know whether it rains because I couldn't attend it. But so we had to do something more close by, and there was no accompanying IETF event. So we just go upstairs to our Cloud9 Sky Bar and Lounge from the Hilton, where we are going to have some little bites and some beers and related things. So that's, we have this place starting at 1700. It opens officially for the public at 1800, and we can stay there and have our stuff till 1900. So this gives us ample time. And this would be the time when we are eager to collect feedback in a relaxed atmosphere on what you like, what you have in terms of suggestions and so forth. All right. So we have full papers and short paper talks. We are not going to do super exact timing, but our chairs are going to watch the time somewhat. So we have for the full papers 20 minutes for presentations, 10 for questions. For the short papers 12 minutes plus 8 for discussion. Interrupt the speaker at any time when there's clarification questions, but keep fundamental discussions about questioning the methodology that was used and so on to the end. And since, as I said before, we do got time, so be interactive. One little requirement is we are being live streamed and recorded by Meetecho. So there's the camera. Speakers should stay somewhere in this range. You can walk around, don't stumble across this monitor and break something, especially on yourself. And use microphones if you got questions. We got a mic here. We have this thing for maybe the session chair, and we have one mic for the speaker. We'll see if we also get a clip mic. So far there is none, but maybe we are going to get one to be able to organize one. The IETF has a note well statement, so we are being recorded and live streamed. So think about which political incorrect remarks you want to make. It might stick with you. Other than that, the IRTF IPR disclosure rules don't apply for contributions made to this workshop, because this is outside the regular IETF. It's just an associated event. So you don't have to state anything about patents you might know about a topic you're going to discuss. Yes, Aaron.
Looks like on the screen is not on. Is there somebody who is able to, if there are any questions or anything, then I'll do that. Or chat room or something. So that screen is attached to a laptop that looks like it's running Meetecho, so it might just be that's the Meetecho screen.
When you just turn it on, which we did earlier, it didn't show anything. Okay, then we'll do it this way.
I just want, if there's anybody who's got questions who are viewing remotely, I want those to get back great. And usually you see your little icon.
You can take a quick look at this and just. So we didn't have anything, any feedback from Meetecho last year when we were streaming this, so therefore. But we can play with this. Brian, do you want to give it a try?
It's
okay. So in the meantime, anybody who has never attended an IETF meeting before, since I see most of the face, wow, this is good. Hooray! Next question: how many of you will be staying for at least beyond the reception and the food for tomorrow for at least one more day during this week? Oh, just of the people who are. So 1, 2, 3. Hooray! 4. Okay, so we have a few people who are. Oh shit.
This would be a great research.
And I thought I would have caught all the all the updates on the slide. Okay. Final questions. How many of you do qualify as students? Also a fair bunch. All right.
All right, so there's no queue.
Okay.
There's no meet echo queue for this, so.
Then we just
If there
then.
are questions, then somebody should walk through.
Okay. So please, Matt is doing this. All right. Thank you. Okay. Then we have a plan.
We have a plan.
Okay. This gets us to our first session. Chaired by Miria. I'm staying up here for a second because I have the first presenter slides on my laptop.
So good morning, everybody. So first session, we have 2 short papers and 1 long paper, all around measurements. And the first paper is actually joint work with some people in my group. And so I actually thought that our student might be coming, but nobody managed to convince him, I guess. So the first presenter will be Randy Bush. He's talking about some measurements they did on the RIPE Atlas platform. And I think this is follow-up work on an IMC paper you had like last year, right? I guess if you don't know Randy Bush yet, you should take the opportunity to get to know him at this workshop. And other than that, it's all yours.
If you know me, you know this is not my presentation. My presentations have a mauve background and magenta type. Comic Sans. This is this was research. The heavy lifter was Thomas Holterbach, who spent time with us doing research at IIJ, moved to ETH Zurich, et cetera, et cetera. So for the moment, I'm a member of the Zurich Mafia. But back to the agenda. For 20 points, what was missing on that agenda? Formal methods. We are standing on quicksand. This presentation's measurement, when serious computer scientists are studying the internet as a behavioral phenomenon, you're in trouble. Enough for a political statement. So this work is a measurement one, as an example. RIPE has 9,800 probes out there, which, how many people here use RIPE Atlas? Yep. If we'd asked 2 years ago, it would have been none. 9,800 probes out there. Which ones should I use? It's a hard choice. It's like being in an American supermarket and there's 5,000 brands of cereal. They're all the same, and the box has more nutrition than the contents. Okay? So the number of probes I can use for a particular measurement is limited. Okay? They limit it because the platform doesn't want you to get too greedy, and you really want to process data from 9,800 probes. Okay? It's hard to know which ones will satisfy a measurement unless you specify, and that's difficult. So finding a minimal set of vantage points that maximizes the chance of seeing what you want to see is a fun game. So they have categorical properties, like this one is behind a NAT, where is it located, AS, et cetera, et cetera. 2 probes in the same AS can see very different paths. ASs, despite the religion, are not homogeneous. Okay? 2 probes in different ASs can see similar paths. The same story, geographic locations and the other things. So let's propose a vantage point selection method based on topologic similarity. Select the most dissimilar vantage points if I want to see from as many places as possible. Select similar ones if I want to concentrate on an observation and make sure it's not just a problem with the probe, etc. Okay? So, how to find similarity? how topologically similar is RIPE Atlas overall, and how to exploit this. Okay, how do we measure it? We define a similarity matrix based on the Jacquard index of the set of IP addresses that the probes observe when they trace route to the same destination. Okay, so Jacquard index is known as intersection over union. I've got a set of trace routes. I have trace routes to the same destination from two probes. There's the list of the addresses they pass through. If they pass through the same addresses, the intersection and the union are the same. So intersection over union is 1. If they are entirely different, intersection over union is 0. If they're similar, you get something in between. So if it's equal to 1, the probes see the same IP path. 0, they see different IP path. Okay? For each pair, we compute the Jacquard index for all the destinations they have in common. So this is something you run every month or 10 over the whole set of probes. And do pairwise comparisons, and of only those that have destinations in common. Then, and by the way, when we do this, when I say we run it, we don't actually run new measurements. There's tons and tons of collected trace route data. Some people are using the Atlas probes to scan the entire internet. We just exploit their data. Okay? So for each pair, we look at the 25th and the 75th and the median, et cetera, and report results in a figure. So this is the ECDF of the probes. This is the Jacquard similarity. This is percentile ranges. You'll notice, I think there's even a slide for this, that about 10% probes are identical, right? Jacquard index of 1. Pretty cool slope. So you can get half at about 0.4. So what we have is a method that we can measure dissimilarity, okay? And let's check that against some reality. We expect two topologically similar probes to be in the same AS and geographically close. So here are probes with the Jacquard index of greater than 0.9. IPv4, the geographic distance, remember, probes, when you set them up, ask you where it is. You put that in there so you can tell there are anomalies. Right, but not that many. And in fact, we've suggested studying some of that, and that'd be fun. So when they're in different ASs with a Jacquard index of 0.9, you can see the index is high. They're in different ASs, but they're still geographically pretty close. Okay? So topologically similar probes tend to be in the same AS. I know we're all shocked. And they tend to be geographically close. So we can take topologically similar probes to think of them as a super probe. Okay, we're exploiting similarity. So if one probe's down, you can run on another similar one. And if your measurement's going to load a probe too heavily, or you're worried about some other piggy researchers loading that probe up, you can throw it over multiple probes and compare the data. Otherwise, if I want to get a diverse measurement, I get topologically dissimilar probes. And if you compare this, what it discovers in topology versus the right random, supposedly random selection methodology, you get 25% better discovery. And that's my song.
Thank you.
Questions?
We have questions. We have time for questions. A lot of time.
I'm a
And I
fast talker.
have prepared some mean questions for Thomas, but now that he's not here. So one question I have is like you make
we
a
have somebody from the audience who wins.
No, not really. I can go first.
The session chair is supposed to have the backup questions.
I have many questions. So you make the statement in the paper that this is better than geolocation, and then you figure out that actually a lot of nodes that have the same similarity are close by. So do you manage to make any assessment if it's really better or not?
You're asking, is geolocation better or worse than Jacquard index similarity?
Yes.
No.
Okay. Did you try to even
other
compare
than,
that?
just a second, let me turn this back on. Other than taking a look at this, the answer to your question is no, we
Okay.
did not dive further.
Okay, that would be interesting to know, actually.
Right. To be
Yes.
honest, this was the tail, as you noticed,
Yeah.
noted in the beginning, of another project.
Yes. And like looking at the slide, so is it that all probes in the second set are actually probes that have been probably moved to the same AS and just not been updated, or didn't look further into that as
No,
well?
they did not move the same AS. You know what AS is.
Okay.
They're in by the addressing in the trace route.
Ah, okay, right. So they just look very similar.
Right.
Okay.
Right.
Now we have a queue.
But for instance, when you look at when RIPE themselves look at the probes, many are residential. Many are sitting behind home NATs, et cetera. So in many, I don't want to say geographies, but many places in the world, there'll be smaller local providers with their own AS. They all have the same upstream.
Yeah, makes sense.
So they look like they're different ASs here,
Mhm.
but maybe the next hop they're not.
Yeah. Yeah. I mean, would probably interesting to look further into that.
Oh yeah,
Yeah,
there's more
yeah,
research to
yeah.
be done here.
Yeah.
Oh, for sure. But I don't think we're going to do it.
Maybe somebody else in the room.
Yeah, somebody else will do it. Here, go.
Then I'll take this for now. Okay, we'll work on the other mic. So I'm curious, how often, what is a good interval to recompute these indices? I mean, routes do change, and so the underlying properties that you observe by comparing the trace route sets do change. And so did you look at maybe what happens if you look at every day, every month, every week, and would there be a sweet spot where you say, okay, this would be a reasonable interval to recompute those things?
If you want to spend a grad student on this, go for it. It's exploiting existing data. So you're not creating new measurements. So you're not doing, you're not being disruptive to the net. So it would be easy and fun to just compute it now, compute it on data for 6 months old, compute it on data for a year old, and look in the change in the data. Easy to do.
I think I have something to tell to my postdoc on that. Cool, thanks.
Hello. I have two small questions. So how do you account for the unknowns, the stars, on the trace route path regarding the set of the IP addresses? And also when multiple IP addresses, so as a router responds on the same interface with multiple virtual IP address, for example.
We're not doing anti-aliasing or any of that stuff. We're just looking at stupid IP addresses.
Okay, so the unknowns are cleaned up or they're not?
They're not, they're ignored.
Okay.
Having stars in both routes does not cause a match.
Mm-hmm. Thank you very much.
And I apologize if I simply haven't had enough coffee yet, but I wanted, well, there will be a slight break later on. So I'd like to understand a bit better what your definition of good is. I mean, implicitly I understand, or implicitly I take away that the aim here is to use the minimum number of Atlas probes to best represent the full span of the internet for some general sense of the internet.
Okay. We didn't. So, if you don't know the size of these sets that I say up here, et cetera, we did not. There's some fun stuff to be done, and yes, we've ignored it. And there's good base work, good theory that we could apply to say to look at measurement minimalization.
Right.
Fess up to not having done that. But if I ask it, please run this from a bunch of probes, throws a bunch of probes at me. If I take the same number of probes, I can get a 25% improvement by being picky.
Right. So I guess what I'm driving at is the RIPE Atlas platform is useful for any number of different types of measurements and different models of universe. And I think you've got a particular model of universe.
This is traceroute.
Yeah. You've got a particular model of universe in terms of what you think is good. By contrast, the work that I was using RIPE Atlas for, that I'm not going to talk about today, I actually wanted to distinguish between individual networks. So I wanted to use it to measure in individual networks, and therefore I wanted things that were more similar to be clustered together. So I'm just sort of driving at the point that this is good and right for a particular model of the universe. Other models apply.
Oh, for sure. Like, this is a trace route view. It's not even a geo view. It's not even an AS view, etc. This is, hey, I'm looking at topology, and with trace route, it's that little corner of the universe.
Hi, Marcelo Bañuelo. Thank you for doing this. I think this is very useful. As an Atlas user, do you think, are you planning to make this available for other people to use, like when we're going to select probes?
It's up on the net.
Sorry?
It's up on the net.
But are you planning to keep updating?
Providing it as a service?
Yes.
No, we hadn't thought of that.
Maybe since Emil is involved or something, you could, because it's very useful when you want to select probes. Having this information seems...
Robert, where are you? There you are, Robert. Robert.
You want me to say yes?
Yes.
Yes. No, it's these are typically the things that we love seeing. Sorry, speaking for the Atlas operations team or development team or whatever that. These are the things that we ourselves were thinking about, some of them, but we didn't do because it's a lot of work and we are not research. Well, most of us are not researchers, so there's good stuff to be done here. But once there is some kind of consensus that this is a good algorithm, only if Atlas ran it inside and gave us the data naturally, that would be great. Then sure, we can do those things. So we even have a contributor.
I'm taking off my research hat. I'm putting on my operator hat, since you seem to like to think operators are your major customer, and I am one. Is as an operator, when I want to look at how the internet sees my data, sees my AS, sees my whatever, I want diversity. And having this as diversity, I want. So it's not just the researchers who would like this. So.
As I said, I'm happy to pick it up and make this a part of your service. That's no problem. The issue that I have, not in particular with this, is that there are like dozens of these kind of things that people want to throw at the Atlas team to say, do this, do this, do this, do this, build in, and we have to look at which ones are, I don't know, more useful or more interesting or whatever they are.
As you're at the mic right now, can you tell something about the selection algorithm you're using right now?
Sure. That's basically what you can say is that give me probes from this country, this AS, this prefix, this and that. But if you say give me 50 from this AS, then the system basically does two things. Randomizes somewhat, so it just says, well, I'm going to look at these 50 probes for you. But the one more interesting thing that most of the people just ignore or glance over when they do such a thing is that we also have to take into account how busy those probes are. So it's nice that you see a probe in Antarctica and I want to measure from Antarctica, but everyone else wants to do that as well. So we actually almost physically had one in Antarctica, but one of the reasons why we didn't do that is that it would be just useless for everyone.
And it's
it would be a
now
nice
floating in
gimmick,
the
but
ocean
basically no one could use it because everyone would want to use it. So I remember a couple of days ago there was a hackathon where some of the participants made a much better algorithm of visually distributing the probe on the globe. So they compared, look, when Atlas picks, this is what you get. When my algorithm picks, all over the place. That was nice, except that in reality, you cannot get those. So we need to expand the network to make that available to everyone. But coming back to this thing, sure, we can do this. We can build in such a thing and say, use the Randy algorithm to give me probes.
It ain't me. It was me. That would be mauve and magenta. Thomas Holterbach.
You're so humble. But I do have a question, though, since I'm standing here. So how would this scale if we had 100,000 probes, 1 million probes? You know, pairwise comparison is n squared. That's kind of difficult.
You're a long way to go. This runs pretty quick.
Okay.
And it's decomposable if you want to use parallelism.
I have a last question. Of course, I was really disappointed that you only looked at IPv4.
Yeah, well, we were looking at the internet. Next try.
Maybe with your experience, you have a guess if you expect that the routes are different for IPv6 or probably kind of similar.
Well, as we know, IPv6 routing is different than IPv4 routing. And I think Jeff Houston said it best a decade ago, is when there's enough money behind IPv6, the IPv6 routing will get straightened out. There's been a lot of interesting work on looking at the difference between the two. You could clearly, trivially run this over V6 versus V4. And if you're looking for V6 probes to use, this is trivial. We didn't do it. That's a common failure. Realize when I give her a hard time about V6, those people that don't know me, is I'm at the first ISP to deploy IPv6 in the world, 1997. So it's trivial to make it do V6.
Okay.
So I have one question before I get out of here, which is there a DNS behavior researcher in the room? You're only 50. Catch me at the break, would you? Because in the knock, we see something really cute.
Thank you very much. Yeah. Can you set this up also? And also that one. Yeah. Oh, that's Randy. Randy, can we borrow this? No, that's the ticket thing.
Oh, you're going to use the clicker. I don't go backwards. I'm going to be my.
So the next talk is not up yet. The next talk is given by Petros Gigi's. He's also looking at RIPE data, and he's looking at user-to-user connectivity. And now I forgot your whole CV. You're a PhD student, right?
I'm a master's student.
Master student, okay. And you're currently at RIPE?
I was there for an internship now.
Okay, you're already gone, okay.
Yeah.
Okay, so I just leave you to your presentation. Do you need help?
I don't know, something's not.
Yes.
This one works.
No, it's not good.
This is not working. Okay.
Okay. So I'll say from the laptop. So good morning, everyone. My name is Petros Gigis, and today I will present the paper characterizing user-to-user connectivity using the.
Break that mic, it's not working. No, nobody's taking. Oh, okay.
I think maybe it's speaker.
Okay, now you can hear me, right? So I'll present the paper characterizing user-to-user connectivity using RIPE Atlas. This is a joint work with.
You're gonna need to use the microphone.
Pretend the microphone doesn't work at all.
Okay.
And stop loading it.
Okay. So this is a joint work with Vasilis Kotronis, Stephen. Emil Aben, Stephen Sroven, and Fondas. And for this work, we had to develop two different tools. The tools are already available as prototypes. And we use RIPE Atlas for the measurements. But first of all, let's look at.
Click again. Now it's working.
Okay. Let's look on the probe deployment around the globe, so we can see that there are RIPE Atlas probes almost everywhere, with Africa being an outlier. And these probes are deployed in hundreds of networks, but we don't have any kind of estimates of the users that are being covered using these probes. So in this work, we focus on eyeball networks. And when we say eyeball networks, we refer to the networks that have the largest users population, that contains the largest user population in any given country. So as an example, an ISP is an eyeball network. And studying eyeball networks is very important and interesting because it's user-to-user traffic. And it's important for real-time communication like online gaming, VoIP, and this depends on how these networks are interconnect each other. So there are many interesting properties that we can study. And in this work, we study the traffic locality. So we try to see if the traffic between two eyeball networks in a country stays inside the country, and if the eyeball networks are direct or indirect interconnected. And this is important for three main reasons. The first one is for security reasons. So if you have an eyeball network connected direct with another eyeball network, you minimize eavesdropping. You also maybe have less latency, and it's easier for a network administrator to debug. And the main questions that we address in this work is to see if RIPE Atlas is deployed in the network with the largest user population in every country, and also study how these networks are interconnected each other. And we had also to think which are the interesting properties we should study and measure and visualize. But also we wanted to see if these properties differ from country to country, and if there are patterns between countries. So we had to create two tools, as I said in the beginning. And using these tools, we tried to answer to this question to find the most suitable way to visualize these statistics and measurements. And for the first tool, we used the APNIC estimates. APNICs provide user population estimates per ASN per any given country. So we selected the eyeball networks using two different thresholds. The first one, we assume that an eyeball network is a network that has at least 1% of the user's population in that country. And we also select one more threshold, the cumulative 95% of population covered in that country. Later, we used the RIPE Atlas API to fetch probes for these networks. And we also convert our estimates of coverage using statistics from Internet Live Stats. So if we have at least one RIPE Atlas probe active in an eyeball network, we assume that the network is covered. On average, we have 90.5% coverage in any given country. However, there are some outliers like Russia. And we wanted to make this more clear, so we visualize our findings. And here is a global map of the RIPE Atlas coverage. We look on IPv4 probes, which are public. So we use a range of colors. With the white are the countries with non-eyeball coverage, and with dark green are the countries with 100% RIPE Atlas coverage. So we can see that Africa is again an outlier. But also we wanted to provide a more useful insight for network operators and RIPE Atlas ambassadors. So we create a more detailed view. Actually, the tool is already available on the link of the bottom. So it's sg-bap.ripe.net and petros/population coverage. So this is a table that we create on a daily basis using the methodology that I described before. So this is a snapshot of 12th of July, and we can see that for the largest eyeball network in Czech Republic, we fail to mark it as a coverage because we have only one private probe. But having one private probe, it's not useful. We need public probes to measure this network. So if we deploy one probe in this network, we increase the percentage coverage in Czech Republic from almost 50% to 80%. And okay, and next we created one more tool. We call it Eyeball Jedi. And the main concept of the tool is to use active measurements. So we use RIPE Atlas probes from eyeball to eyeball, and we do trace routes from eyeball to eyeball networks. And we look on the properties like if a trace route path stays inside the country, and if a trace route paths traverse other ASs, if yes, which ones, how many of them. And let me give you some more details about the implementation. So we do monthly trace route from eyeball to eyeball networks. And for the probe selection right now, we use a very simply methodology. We select the closest and the farthest probe from the country's capital to try to expose the AS diversity. And we use RIPEStat to map IPs to ASs. We support IPv4 and IPv6. And to geolocate the trace route path, we use OpenIPMap. In order to, as I said before, to visualize the statistics and the findings, we had to come up with a visualization. So we created the AS to AS matrix. The AS to AS matrix is a tabular structure. Each row represents an eyeball network as a source, and each column represents an eyeball network as a destination. The size of the cells depends on the APNIC estimates, and the color of the cells represents interesting properties, like if a trace route path goes out of country, stays in country, we have ripe atlas covered. Are there any inconsistencies between probes? I forgot to mention that we select 2 probes per eyeball network, so we have 2 against 2 other probes in the destination eyeball networks. So we may see different trace route paths. And we use a basic metric. So we select, as an example, the green boxes, and we divide it with a whole area of the AS to AS matrix to find the basic metric percentage. And next is an example of a eyeball Jedi for Canada. This is a snapshot of 1st of April. So we can see that almost 47% of the trace route path stays inside the country, and only 3.1% is going out of country. We have some inconsistencies, and we like to measure small networks. We also investigate the direct and indirect paths, and we use the border to distinguish the direct and indirect paths. So with white borders, it's the direct eyeball to eyeball interconnection. So for Canada, we found out that almost 41% of trace route paths between eyeball to eyeball networks that we measure is direct paths. And next, as we are in Czech Republic, we couldn't resist and measure Czech Republic. So as I said previously, we like to cover the biggest eyeball network. So that's why you see the white boxes. And we also see here that almost 10% of the trace route paths between eyeball networks, they go out of country. We like to cover 32%. We do not measure 46%, and the direct path are 17%. We also measure Australia, and this tool measures right now 104 countries, and it's available on the link on the bottom of the slide. And as we can see in Australia, between eyeball to eyeball interconnections, we see that every trace route path stays inside the continent. And indirect and direct paths are 25% and 29% respectively. In this work, we have some limitations. So first of all, ripe atlas provides a biased view of in-country connectivity. We measure trace route paths and not traffic volume. We don't have ground truth about the IP level and geolocation accuracy. And we also face the same difficulties with other works like IP to AS mappings. And we plan in the future to use tools like Mapit to improve that. We also measure on layer 3. We don't have any layer 2 visibility. And we are looking for ground truth inference for for the APNIC estimates, and also for the way that we define the in out of country path. So as a future work, we plan to move from prototype of this tool to a fully fledged tools and make them publicly available to the community, to the network operators, and also to the researchers. And we want also to gain visibility on eyeball to our neighbor country eyeball traffic. So as an example, we want to measure the eyeball networks of Netherlands against eyeball networks of Germany. And we also want to measure eyeball to popular CDNs. We are also looking on more sophisticated probe grouping selections, and we look for collaboration and contribution on this. We need also to validate our inference about IP to AS mapping, the geolocation, and as I said before, we want to integrate tools like Mapit on our methodology. So for conclusion, we estimate the RIPE Atlas coverage in eyeball networks, and we presented a prototype of the eyeball ZI. The main aim of the tool is to measure and visualize aspects of user-to-user connectivity per country, and the tool is developed to help users and operators to discover interesting interconnectivity artifacts in the countries they live or they operate. The tool is available again on that link. And our work is based to probe measurements using RIPE Atlas. We use the APNIC estimates, and we are very thankful for APNIC that provides such kind of statistics. And we use IP to AS mapping from RIPE-STAT, and we do the geolocation using OpenIPMap. So you can view the tools. As I said, they are available. So if you have any questions.
Thank you very much. I have two quick clarification questions. So one is, which kind of trace route did you use?
We use Paris trace routes.
So TCP trace route?
Yes.
Okay. And the other one is, you have this inconsistency number. So that's when you do two measurements and they show different results.
Yeah.
Okay.
There were sometimes that we see that a trace route use a probe use a different upstream provider to reach the same network. So it may depend on the network. As an example, Greece, because I know the ecosystem in Greece, for a network, they divide their network in two parts, the north and the south. So they use two different upstream providers even to reach another network.
Okay.
So that's why we see the inconsistencies.
Go ahead.
Okay, do we have a... I'll try. Does this work?
Yes.
Okay, so if you bite into it, then it works. I had a question. You had for your definition of an eyeball network, you had this magic number of 1% of the users of a country. Where does this number come from? Is this intuitively it feels too small to be representative?
Actually, we want to study in a fine granularity, and we wanted to make a visualization, but it's easy for someone to view it. So if we lower the threshold, we will end up to something like the IXP country today. We'll have hundreds of networks. So
in other words, 1% is already a pretty large number.
It's a large number.
No, no.
So
I would have said if a network is representative for a country if it covers 10% of the users or 15%, not just 1%. This is what I'm wondering about.
So that actually goes in line with my previous question, because if you saw these inconsistencies because some of the network providers split up the network, then you just randomly saw it at some point, and in other points you might not have selected any nodes that would have shown the same behavior. So maybe you need to measure more probes within a network to get a better view.
Yes.
That's also kind of what you're saying, right? Yeah.
Right.
Okay. So I have, I guess, a little bit of a meta question. I'm wondering why you started by focusing on end user to end user traffic patterns. Now, I work for a CDN, so maybe I have a distorted view of the world, but it seems to me that most people's interactions with the internet involve a third party, a service provider of some sort, whether it's email or they're collecting or a website or something. So why is user to user direct connectivity interesting?
Actually, there are many applications that they use user-to-user connectivity.
Can you give me a couple of examples?
Like
VoIP? Direct end-to-end VoIP? Yeah. Is that, are you, that's a, sorry, now I'm arguing with Magnus, but.
And
so yes, you have a destroyed view of the world.
Yes, yes. Well, all right. So I tried to preface my remarks, but it just seems to me that there's why start there? I guess that's the question. I'm not saying that there isn't that traffic, but what makes that interesting?
And this is a first step. So we plan to measure against CDNs, but measuring towards CDNs is a lot of more complex.
It's a fair answer.
This is actually, oh, wow. Okay. Hello. This is actually more of a comment than a question. Because you pointed out that you're looking, like future work is integrating border map and or map it. I'm wondering how much of your inconsistency actually comes from inaccurate AS boundary inference, because AS boundary inference is a well, I mean, like if you look at the prior work and map it, right? AS boundary inference is a really hard problem, and doing the dumb thing ends up having you get like wildly inaccurate estimates for certain topologies. So when you see an inconsistency, some of that could be either zoned routing or different routing policies where, you know, you're, as Randy pointed out, you're making the common, it's a common fallacy of an AS is actually an internally coherent thing. But I think that some of it could be your border inference, or am I missing where that incoherency is coming, or where that inconsistency is coming from?
It may be the border, as you said, but also it can be wrong geolocation. So
okay, yep, right. Which is also for ripe atlas probes is best effort faith, right? So
yes.
Okay, cool, thanks.
And I'm having kind of the same last question again. Did you look into IPv6?
Yes. Yes, we looked. But currently we have on the online tool only IPv4, but soon IPv6 will be there. And we plan to make it like a fully fledged tool.
Okay, thank you very much. Anna, are you bringing your own laptop? Yes. Okay. So while Anna is setting up, this is really fun. Can you hear me?
No, no.
Because it's off. Okay, now. It turns off again all the time. Okay, so the next talk or the next paper is a full paper, and it's from EMesh, and he can unfortunately not be here. I guess that's the one travel grant that didn't work out, maybe. Jörg? That's a student, okay. No, okay. That's some, okay. So he couldn't come, he's at CISC Rice in Sweden, and now Anna Brunström is presenting instead. She's a professor at Karlstad University. And you've been kind of working with them together and doing some measurements, right? You're basically involved in this.
I can answer that questions, I guess. So yes, so Ian could unfortunately not be here. He's in Australia for family reasons. So he sent his apologies, and I will try to introduce his work on SheSpy, which is a lightweight measurement platform, which uses Raspberry Pis as the measurement nodes. So this is a platform that Ian has been working on for the last 3 years or so. And this paper, SheSpy Research Results and the Regulator, kind of gives some background on this work and summarizes a bit the different measurements that have been done and what it's looking forward to do. So if you've looked at the paper, you've seen that it covers a number of different aspects. And this work has been done in the context of READY, which is a national project in Sweden with the research environment for advancing low latency internet. And Karlstad University is a partner in that project. So in that sense, I have heard about the SheSpy a number of times. We have one of the nodes located in Karlstad, but I have not been directly involved in this work or in the measurements in the paper. So this is all Ian's work. So I will do my best to try and still introduce it.
And also one interesting thing to mention is maybe that this was first presented at the RAIN workshop 2 years ago, also co-located with the IETF. And now we're happy to actually see some results here.
Yes, so if you were at RAIN, then Ian introduced the platform there and talked a little bit about it. So Ian has sent me the slides, and it has 3 parts. So first, some general aspects about the measurement background for the platform and the context in which it has been developed. Then some examples of the measurements that have been done up to now and the types of measurements that you can use the platform for, and then some future directions. So SheSpy targets home networks. So the idea is to try and capture the internet performance as you see as a home user. So you would put one of these SheSpy devices in the home and measure performance from there. So the greater context is kind of that you see internet at home as a utility, and then of course we need to have an ability to monitor and follow up on this. Measuring from the home vantage point is also something that is typically not so easy from the external tools that the ISPs may use to monitor networks. So it's in that sense complementary to that type of measurements. So there are of course a lot of different measurement platforms and measurement work out there. So as I said, SheSpy targets measurement from the home network. So in that sense, it has similar goals as other tools that have also looked at home networking, such as Phantom, Netlyzer, HostView. Already from the beginning, Ian has been in context with the regulators in Sweden, Post and Telestyrelsen, the PTS. So it's also an intention here that the monitoring should be useful from a regulatory perspective. And Ian is working together with PTS to try and develop the platform in that way. The need for using the measurements that we do as researchers as a measurement community also for regulations and influencing policy was something that was discussed also at the AIMS workshop earlier this year. And of course, the different regulators are also doing efforts in this area. So in Europe, we have BEREC, the board for the European regulators, that have looked at how you can follow up on the directives for open internet that we have in Europe. In the US, you have FCC, which has the Broadband America measurement campaigns to try and follow up on internet performance. So this work with PTS kind of ties into these aspects. And the regulatory view is also something that has been discussed in IETF in the IPPM measurement group. I think there was a draft discussed in Chicago that related to this from the net neutrality and regulators perspective. So SheSpy, will it solve all these problems? Of course not. It's just one attempt here, another measurement platform to make some contribution in this space. And the way the platform is set up is that you write your tasks, your measurements are typically put together in Python, and then the platform has mechanisms so that the results get collected in the database on the Pi nodes, synchronized to a central database. which collects all the measurements. There is a scheduling system so that you can indicate the schedule for when your test should be run. And there is also a dashboard for the tests that are available with GSPI. So there are like 15 measurement tasks defined so that you can, as a user, see the impact of your, the quality of your connection and the results of the measurement. So there is a further slide on this later on here. And of course now, Ian is looking into also how to design the specific tests that the regulators would be looking at here. And of course, then we are talking about things like, are you doing traffic differentiation in the networks, or the flow prioritizations? Do we treat different applications in different ways, and so on? So the things that you would need to follow up on the regulatory, from a regulatory perspective. When you do measurements, you can have different approaches. You may do the crowdsourced approach, where you have a lot of volunteers that download your software, and you get a lot of measurements, and from that you derive your statistics and your view of the network. So this is not the goal of GSPI. So the idea here is rather to try and very carefully select your measurement points so that with a minimum of nodes, you can collect the information that you would need to kind of get the view of the network and follow up from the regulatory perspectives. And having a long-lasting measurements. And there's also been, Ian has also focused quite a bit on specific events, on busy times when you have some popular things that the regular user would like to take part in or to view and see how the network works under those conditions. And of course, if we're now going to put this platform in the home users and run it from there, it's essential that it's trivial to install and configure. So from the regulatory perspective, you need to follow up on different directives, which are often quite vague, maybe in the way they are specified. So you need to be able to define how to actually do the follow-up on this, and to then also have some method to see that the ISPs or other actors, if they are not following this. So in Sweden, at the moment, what PTS does is basically it uses surveys. So it sends out surveys to a number of users to see how the quality of the network connections are. It also sends out surveys to the operators to have them report on if they do, what type of traffic differentiation they may use and what special services they have. So the idea here is the goal here together with PTS is to also support this with measurement information, where you can actually detect some of these things and see if what you get into in your surveys is also what the users actually see in the network. So if you're now going to measure from a perspective of a regulator and use this maybe to enforce policy, then the fairness of the measurements is one key issue that Ian is currently thinking about, and that I think will also need more thought here. It's not that there are a lot of this is still a work in progress, even though it's been ongoing for a while. So when we as researchers do measurements, we are a bit opportunistic and we look for some particular aspect, and we may measure, and if we catch that, this is maybe serving our purpose. But if you're going to use it more from the regulatory perspective, you have to be fair to all the different operators and see that you capture a correct view. So how do you do fair measurements? This, I think, is an open issue. Do you need to measure the same number of traffic per operator? Do you scale it depending on the size of the operators? Do you need to have the exact same time when you do the measurements, and so on? And what will be accepted by the different actors in the that are involved in this issue? So this is also something that in Sweden there are ongoing discussions right now between the different actors involved in this space on how to define measurements that all can agree on actually are representative and can be used to measure internet quality. Okay, so this was a bit of the background and the general scope that GSPI has been developed in. So now some examples of the type of measurements that Ian has done in the past. So the platform has so far, of course, also been used mainly for the research purpose so far. So there are three types of measurements that you could do in the platform. The first, of course, is that you can take your SheSpy node and then you can measure to some service at the internet. And what Ian has mainly been looking at in that context is to video delivery. And in particularly, he's trying to look at stalling events. We all know that video download is a complex aspect, so you have a lot of interactions between different aspects, between the different algorithms involved, between the networking effects. So he's been doing capturing measurements here to try and identify which one of these things that you can measure in the network actually has an impact on the stalling of the video, and applying various statistical techniques to try and isolate the different components. And for this work, he's using some of the video sequences from the video quality expert group, which has a pre-rating offline, so that you have a baseline for what the video should, type of rating the video should get if there are no impairments over the network. Another type of measurements that Ian has been doing is between different SheSpy nodes. So then you have control of both the server and the client in the measurements. And he has been doing, for instance, basic delay measurements. So for that, he uses TCP-based measurements, so measuring either in the handshake or the teardown of the connection. So you can measure between the SYN and the SYNAC, and this, of course, gives you a delay measurement for the network. And as you have control, you can also remove the delays from the server processing or the client processing. So this is an example graph from the paper illustrating some of the measurements from the platform. So the blue here is basic ping measurements. And then there's the delay measurements that are based rather on the TCP measurements. And you have the green one when you have not removed the server processing delay, and the red one when the server processing delay is removed. And if he's trying to do this, of course, also not just once, but over time to capture the stability of the network. And one of the future directions that he's also looking into is using this for multipath, and also doing multipath measurements over SheSpy, where you could then use this as input for path selection if you have his historic data here. Then the third type of measurement that Ian has been doing is using multiple SheSpys to monitor some events, some key happenings. In this case, he has looked at boxing matches that are very popular, so a lot of users go online at the same time, and then measuring over time, so that you can see here is an example for one of the boxing games that they monitored. So here is the time up to the match. You can see that the delay in the network is quite stable, and then the closer you get to the event, then you actually see that you have some impairment for some of the providers of this game. And by trying to measure from multiple SheSpy measurement points and also with multiple measurements, he's trying to separate the different aspects that contributes to the delay here. So we have both the basic ping measurements and then also the measurements at the HTTP level. So to try and separate the effects that comes from the server being overloaded from the effects that come from the network being overloaded. And this in general, of course, is not so easy. I mean, you see the end effect, but to also try and isolate what is actually the cause of the difference. So he's trying to then look at the combination of these different measurements to isolate the different effects. As I mentioned, there is also a user interface available for this SheSpy platform, and it has some different levels. So there is a interface for the more tech-savvy users. So I think it's very hard for you to see now. You have this figure also in the paper, but this one illustrates some of the outcomes of some of the tests that are defined in the platforms. There is like a speed test-like test. There is a HTTP download of one of the Alexa sites. There is some DNS lookup test, I think, and you also have some statistics on the SheSpy platform itself and the load on the measurement nodes. So you can get some quite detailed statistics on the tests that are being run. As this is intended to run in the home network and also be for the average user, Ian has also worked on trying to have a more simple interface for the non-techie user. So this is an attempt to illustrate how well your network is working. So this is kind of your speed of data coming in, and in order to meet different types of applications, you would need different levels of water to be sustained here, and if it's met, then you have a happy duck in your bathtub. So I'm not sure if this is easily interpreted by the end user, but this is one of the yeah, finally we're right. So, but this is one of the aspects that Ian is also working on in connection to the visualization. And